So welcome, ladies and gentlemen. I know it's the last session of the day, but trust me, I told you I'm the least technical guy around here. You won't be disappointed. I've had the opportunity to see Jens' presentations, whether he's talking to the Department of Public Service, whether he's given a presentation to Commissioner Christian and his team. I was able to sit in on a presentation that Jens did in November to the U.S. Department of Energy, and quite incidentally, in December, they came out with their report that Alexis McKittrick talked about at noon. I want to believe that there's a piece of you in there. Yes, there. Yeah, no, don't. I'm not buying that. And so Jens most recently gave a really great presentation on the benefits of the geothermal to the grid, convinced the Rochester Gas and Electric at New York State, NY-GEO, New York State Electric and Gas, and the DEC of New York State about the value of the grid. So he is no stranger to giving excellent presentations. And I've always asked myself, man, he's so busy. He's the owner of Buffalo Geothermal. How the heck does he get the time? And I finally figured it out. We were supposed to have a second speaker, but he is ill. He happens to be the guy that takes care of business when Jens isn't there. And it's I just want to mention his name because I know he put a lot of effort into this presentation. Johannes Roseman is with us in spirit. He's Jens' Vice President of Operations back in Buffalo. And please let him know we recognized him here for his effort. So I am really proud to introduce Jens. He is an international geothermal expert. He's got more certifications than I could even remember, and he'll tell you what they are, I'm sure. But please give a warm welcome to our New York GEO President, Jens Ponikau.
I took the jacket off, and you can see it's time to work now. Yeah, unfortunately, Johannes is not here. Johannes is our VP of Operation. He's our mechatronic engineer. I stole him away from Porsche in Germany. He was developing the drivetrain and the two-speed transmission for the Porsche electric car there. So, but we figured we have more for his talent with controls. We have more. It's actually more fun here. It always helped that he was my wife's nephew, so that became a family affair. So, anyway, unfortunately he's not here, but he's obviously crucial in here. So I just want to talk. There we go, mechatronics engineer. So let me just go where this is going, and this might be very provocative what I'm about to say to you, because it teaches you something different than what other people might want to think about hot water generation. How hot has the water has to be? 140. Okay, you heard how I phrased this. How hot does the water has to be? 160? Is there any code which says the water has to be 140? Okay, good. Is there any code which says the water has to be hot 40 in a storage tank versus produced at 140? Not either, huh? Why are we doing this? There you go, Nella. Okay. Is there a single, yes? Oh, that's interesting. They do. Why? I don't know either. Because I spent a few days of my life trying to find a single case in the entire world literature which has been proven to be related to the hot water. Cooling tower, evaporation, yes. Hot water, air ducts, dripping water in there, giving breeding ground, yes, absolutely. What is the biggest case if you look for the CDC, Centers of Disease Control, for the hot water? Is actually weekend homes and or rental homes, Airbnb, with a hot tub, which is not sanitized correctly. And then you sit there as a temperature comfortable for you, which is probably about 105, 106, 107 degrees, and you're right above sniffing in the evaporate after it breeded there for a couple of weeks and nobody took care of it. That is actually giving you the highest Legionella cases. Hot water? I yet have to find a single one which is linked to it, to be honest. I had an outbreak a few years ago here in New York City, right? And that all came from a hotel tower in the Bronx. And then there were a couple linked at NY-GEO, actually. And then they found a patient with Legionella out of their development, Melrose, and they also found the same strain in the hot water. But they also found the same strain in the cold water. So they couldn't link it to anything there coming out of the hot water system. It's actually in the cold water. And if you actually find Legionella in the hot water system, it's usually in the branches when an apartment hasn't used, was not occupied for a while. And the water is sitting there at maybe 108 degrees, 107 degrees, 100 degrees, 110 degrees in one of the branches to the apartment, but it's never flushed through for weeks to come. Then you find high concentration of Legionella in there, and you flush it out, and it's pretty much gone. But the normal use there, the evaporate needs to be finer to get deeper into the lung. The real droplets coming out of the hot water system, they don't get deep down in your respiratory tract enough. Anyway, make a long story short, this is the Legionella chart, and you might recall that this is in Celsius. Most literature in the scientific the most scientific literature is in Celsius, and it pretty much shows you that this is the perfect growth area for Legionella. So as soon as you're above 20 degrees Celsius, you enter the optimal growth with Legionella. Legionella is found in every single water well in the United States, by the way. It's in our cold water supply. It's something we need to live with. And all the people on well water, by that chart, should get Legionella's disease, but they don't. Legionella takes about 2 weeks to grow to concentrations and multiply itself that it actually becomes dangerous. So these are the charts here. You got to understand that Legionella does not grow pretty much above 120 degrees. Everybody agrees on that. That's why it's permissible, absolutely, to have hot water being made instantly and sent up to the building. But if you store it for a longer time, even at 120 degrees, it does not grow, it does not multiply anymore. Once you get up to 100 and, above 122 degrees, it actually kills it. 90% kill rate. It takes longer, about 2 hours, for Legionella to die at 122 degrees. Everybody agrees on that. So I have no idea who made up the 140 degree rule. But this is where the point is the CDC recommends it because it gives them, less liability. But that's really not the point here. I just want to sensitize you that there's really not much, any kind of scientific background or any must-do rule to require that. But we're dealing with it. And some of your clients probably mandate it because they don't want the liability. I just want to give you the background. There's really nothing out there which says, yes, it's a recommendation by the CDC, it's a recommendation by New York State Department of Health. Sure. But they also don't understand how difficult it is to make that water. So, anyway. So, here now, this is actually one of the neater charts, and I found it at a plumbing contractor in England who brought up that chart, and I found that was very intriguing because it shows you one thing. Legionella takes time to grow. Once you start to turn over the water 50% a day, it doesn't have enough time to grow and to get concentrations. In other words, this is a turnover rate in percent for the tanks, and there it doesn't matter what temperature you have, you essentially continue to flush it out. You refresh the water so quickly. So multifamily buildings where you have, I don't know, 10 turnovers a day, doesn't matter what temperatures it's parked at. And a lot of times I would argue you have also Legionella, even if you sterilize the tanks, the cold water supply has Legionella in there. Now you send it through the mixing valve, you send it up to the building and it ends up in a branch there. Now it sits there for weeks and can grow under optimal growth conditions. So it's a tough cookie to do, but us sterilizing the tanks with temperature doesn't really do that much. And there's no scientific background for anything. Okay. Why do I really like and want hot water and make hot water via GEO? Well, first of all, it's 17% usually, at least, on average in residential systems. It's up to 40 to 50% of the energy a building uses in multifamily, specifically in affordable housing, just to the high occupancy rate. And so I want to explain one thing, and this is very important. Every single multifamily building I've dealt with, whether it's in Buffalo, north of Albany somewhere, or in New York City at almost northern Texas climate, is cooling dominated. I reject more heat into the loop field over the season than I pull out. So I want to make the hot water because it helps me to cool the loop field, specifically in the summertime. And the loop field design is always on the dominant load, which is always the cooling load. That means I need to design my loop field larger for cooling, not for heating. So I want the equipment on there. And I make this point later again. I tell every developer, if we're building a geosystem for you, your hot water making equipment and is all free. Why? Because I save so much money on the loop field, which I otherwise have to make bigger, that I can give them the entire tanks, hot water making, everything else free. So I want the hot water in the system. So this is an example. This is Riverhead. These are like 10 looped together residential homes on a mini district system that was National Grid's demonstration project. And you can see here, it was about 72% heating and 28% cooling over the year. However, this is what the loop field saw. It's almost a balanced loop field because in the summertime, you not only have the heat you pull out of the house, you also have the compressor heat you need to reject. And in the wintertime, you don't need all the heat from the loop field because you have the compressor heat now also ending up as heat in the building. In other words, when you have about a 70-30%, that's kind of the rule of thumb, balanced building in heating versus cooling, you have 50-50 going to the loop field. If you have any other higher ratio, which is in multifamily buildings the case, you're immediately overloading the loop field with heat, and you need to make it larger for cooling purposes. And that gets even more difficult in New York City because, groundwater there is about 10 degrees colder than it is up in Buffalo or north of Albany. Okay? So, the bottom line is, and this is just to exemplify, you're putting, this is the building load, and this is heating, and you're pulling heat out of the loop field, about 2/3. This was the compressor power there. This was the fan power, and this was the pumping power. All ending up as heat directly or indirectly into the building. But we're only pulling about 2/3 of it out of the loop field. This is very different in cooling mode because I have to reject the compressor power too, and that's actually measured in this Riverhead project. Can you see? Am I in the way? It's good? Okay, you kick me. Yeah, okay. So it's just to emphasize, we want the hot water on there. This was without the hot water, but that was only 70% heating, 30% cooling, because these were all residential projects on Long Island. Okay, so this is an example. Lockport Housing Authority, 32 apartments, 8 apartments in each building block. And we kind of did the anti-district here. We actually, the loop field is between the walkway and the building, right here, here. We didn't use any of that stuff. We didn't want to deal with the landscaping and everything else. We put it right next to the building, 4 boreholes going into each building block, call it a day, not looped together. So here, the domestic hot water is almost the same as for a residential building, because you only have 8 apartments on there. You have a little 2-ton water furnace unit here, a storage tank. You come in from the loop field, you have a couple variable speed pumps here. It sends it all out to the building, to all the air source heat pumps, little console units. And you just, turn on that heat pump whenever that tank is below a certain set point, make the hot water. Big deal, right? Simple. I agree. Okay. What about when the buildings get a little bigger? That is Pierce Arrow. It's the largest retrofit so far in New York State. The old Pierce Arrow historic building in Buffalo, New York, about 120 apartments and a larger restaurant. And so it becomes a little bit more difficult. So we use now high temperature heat pumps here. These are 3 water furnace high temp heat pumps, vapor injection heat pumps. So we can get the water going in here up to about 145 degrees. And yes, we can run them at 140, but we don't do that. We run them at 125 for the reasons I gave you. And so there's a design here we implement to increase the efficiency. So for example, this heat pump is dedicated to 2 preheat tanks. It brings the water up from, let's say, 50 degrees or 40 degrees to 100 degrees. And then those 2 tanks only need to make up the difference of 25 degrees. The beauty is that this heat pump here, to make water only 100 degrees, run at a COP of 3.6 on average. The other one here, they run at a COP of about 2.9. But it's a little trick to do the vast majority at a higher COP. This heat pump there doesn't do anything. It has a 3-way valve. So whenever we have an issue, a mechanical failure with one of them, this one can either heat this tank or this tank. It can switch between them. It's like how we design in resilience. You don't want to have an emergency where 150 apartments are on there. Okay, so controls, as far as I care, relatively simple, just off the shelf. That's where Johannes comes in with his. Let's design this. So this is how they look in real life. Here are the 3 stable Eltron tanks, indirect tanks. There are solar tanks. There are 2 heat exchangers. I actually piped together here. They're designed originally, they're from Germany, and they are originally that the upper tank is solar and the lower tank is a backup boiler. But we pipe them together so we have a higher surface area. They heat better and can transfer the heat better. Again, the 3 heat pumps here. That's it. We have 2 mechanical rooms for 120 apartments that way. And again, my trick is to say, I give this to you for free. I make all your hot water, all your mechanical room, all for free. If you include hot water in the whole thing, why wouldn't you? Okay, so this is one example. What about that? Whoa. Now the fun starts, right? NY-GEO. So this is Jackson Houses. This is Jackson Houses, and in the Bronx. So we're doing the 2 pilots there for NY-GEO. And these are the 17 high rises. These are 7 of them. And I warn you, when you deal with affordable housing, you got to make sure 100% that you measure the hot water. Because they tell you this is how many people live in there, and you take that number times 2 or 2.5 or 3. And this is your hot water usage then. So when we actually measured, that was about more than twice as much. And so what do? This is their water profile in one of the buildings. We're talking 6,000 to 7,000 gallons a day. And this is their profile. Remember when the textbooks show you the profile is like going up in the morning, then normal, going up in the evening, then normal, right? This is a weekend day. This is a weekday, almost the same. And you have essentially a larger peak. So this is one of the buildings, the same building, same occupancy, now suddenly has twice as much. Until today, I don't even know why. Whoa, now you have your real awakening. And look at this profile. You have a peak which starts at 6 in the morning, and that peak keeps going for the next 12 hours. How are you going to heat anything like that? And then you have a super peak at the end for 2 or 3 hours. What goes up another 40%. This is real life. And you better measure that before you get into this. Yes?
Were they using steam?
Yeah.
Can you repeat the question?
Can you, whether using steam? Yeah. That's part of their problem. They're using steam for the radiators. The tenants don't control, they don't have a thermostat, so it's like, you know, it's like Russia. You regulate the temperature with opening and closing the window. And you can tell it's a NY-GEO building because you walk around and all the windows on the coldest day of the year are open. And next thing you know is, the problem is also that now they're converting over to hot water, and the biggest saving comes from just decoupling the hot water from the steam system. Because the steam is made centrally in each of their developments. They have one big boiler plant where they make the steam. Then the problem is that the heat exchanger from steam to hot water is in each building. In other words, they have to run their entire steam plant running all summer long just to make the hot water. Can you imagine how efficient that is? But they do. That's part of the problem we're trying to solve. Okay, so that's the problem. There is only one peak, and that lasts you about 15 hours. And the problem then is, if you're now trying to solve that with storage tanks, those tanks will be empty, and then the real peak starts. You're out of luck. So what do? Any suggestions? So your conventional wisdom changes from, let's create storage for the peak, to say, no, I need to have the capacity to essentially make all the hot water at all the time with the heat pumps. There's no storage. I mean, there should be storage, don't get me wrong, but boy, that storage can be very quickly depleted. So, we're going to have fun here. This is it's a prototype. I saw GT there. Is JT here? Water furnace? No. What do you see there? Any ideas? So I let you guess. I showed it to a couple of manufacturers, engineering, and they couldn't figure this out too. So don't feel bad. So what is the entering water temperature into the heat pump? Oops. There we go. So cold water in is 46, right? What's the hot water out? 150. Hey, 100-degree lift. Isn't that wonderful? How is that possible? Pardon me? Fire? There's a secret electric heater built in, right? This is with 410A. Mm-hmm. Ooh. Not we're getting there. Yeah. I mean, it's kind of fun to play with it, to be honest. But the point is, look at the high pressure. Is that high? No. This baby is humming. So there's some technology coming where we treat this is a 30-ton heat pump, and we're making instantaneous hot water for NY-GEO. So, and we have a second one there because we need a lot of hot water. I'm just telling to you where the technology is going potentially. The pressures are not high. Pardon me? No. You just send it in cold and it spits it up hot. There's no, it's a constant capacity. So, yes. Right now, under those conditions, with 154 degrees or about 3.25. Well, there's some interesting technology coming out. Let me say that. So yeah, we call them the prototypes. We're boarding in 34 of them. So, anyway, yeah, I just wanted to point that out. That this is very unusual, but this is where you can get with innovative design. So we're essentially making instant hot water for those high rises. It's possible. It's coming. But it requires very sophisticated controls, and then you get the heat pumps under some operating conditions where they're extremely happy. Yeah. Pardon me? The GPM for this 30-ton unit on a load side, 6.62 GPM. Mm-hmm. It's crazy, right? Mm-hmm. Half a GPM per ton. Hmm? Mm-hmm. Yeah. Yeah. Anyway, just want to give you examples that sometimes you have to be innovative. I got to give some Waterfront a little credit. They were saying this is totally crazy, but we're in. So, and it's working. Anyway, make a long story short, this is coming, in my opinion, because what they still cannot overcome and explain. This is a condensing temperature. It's about 130 degrees, and we're making water which is 150. So, but anyway, just to give you a little teaser what's coming, we get technology out there which can do all this. So, the key is, or what we learned is the key, do not mix in cold water. Do not destroy the stratification of any tanks, of any storage, of anything. Conventional wisdom tells you you're going into a tank, and a lot of people would dump the cold water return into the cold water supply, right? The hot water return from the building, from the circulation line, into the, do not do that. Why would you heat up all that nice and valuable water, and now you mix it down again? Now you have to heat it up again. And it costs you a lot of energy to make water really hot. That's why even the mixing valve is not very efficient. You make it up to 140 to cool it down again to 125 or 120. Otherwise, people can scald themselves. So the trick is, you send them all into this unit here, and you control the water flow through those units, and you send them pretty much directly into, they had designed in an electric quote-unquote backup tank, because they say this is never going to work. This cannot work. Sure, it does work. We don't need the electric tank. So, but the point is, let's say there's a demand for water, and this is fluctuating, sometimes 3 GPM, sometimes 9 GPM. You have the hot water coming out of the heat pump at 140, and it goes directly to the mixing valve. And what is, if they need more water, if the demand is higher, it draws the other 3 GPM through the series of tanks and sends it to the building. If you have lesser amount of hot water, it replenishes, it goes back to the piping system. This is why the arrows are 2 ways here, and fills up the tank backwards again with 140-degree water. And that way, you have the hot water pushing out the cold water until the last tank reaches a set point and the heat pump shut off. Or you have a higher water demand, then it draws from them, it makes already 6 GPM, and the second heat pump can kick in, makes now 12 GPM, and if you have above 12 GPM, you can now kick in a little bit out of your water storage. The key is not to mix in the cold water anywhere, no matter what you do. So we're not having a 180-degree boiler here, which it doesn't matter how much you mix in. You always get 130, 140 degrees out. This is different. We don't have that luxury anymore. Heat pumps are different. So the important, again, is to make sure the hot water is piped in some of the tanks. So now you dribble in the return line. You mix 115 degree coming back from the building with 140. You keep 130, 135 going out if you need to. And if those tanks recognize they drop too much, you kick in the second heat pump and you just go backwards. Those tanks turn over, by the way, at 12,000 gallons per day. These are 500-gallon tanks. They turn over 6 times a day. Who cares? Doesn't matter what temperature they're parked in. But, trying to explain that. They don't want the liability, so they get the 140-degree water. Yes?
This is still, you're talking about the system. This is the one that's the NY-GEO system, right?
Uh-huh.
I've done some work on NY-GEO buildings.
Okay.
They don't have cooling, so this system is
This is heating only. Only hot
heating
water.
only for
Heating only hot
domestic hot water
right now. The system is designed to put the rest of the building load on there if they want to expand it. But they didn't have the money, and they have a mandate to reduce their emissions by 40%, as you know, by 2030.
Understood.
So that way, we show them a way how they achieve that mandatory goal, their policy goal, and they are on GEO, and they save over 40% of their hot water, their energy. So that's why, and they don't have to go into the tenant apartments to do that.
Right.
That's the trick.
Well, what does your bore field look like for a heating-only system of this capacity?
About 10 boreholes at 500 feet,
What's your spacing?
about 30 feet. It has to be spaced wider.
Yeah.
It wouldn't work if you do 20, by the way. They have one with 20 and it's not working.
I know.
I know too. But that's really the point is that in a heating and cooling building, the distance can be 20 feet. Beyond that, there's no gain anymore. In this, I was surprised myself that you have to go a minimum of 30. Otherwise, they constantly steal heat from each other later on.
When you guys drilled the boreholes, what were you drilling into, bedrock, or was it?
Yeah, it was all bedrock.
Okay.
I mean, after
10 feet.
yeah, 10 feet, and the other one was like 40 feet.
Yeah.
Yeah. And then we had, we have underground rivers there in the Bronx. We had conductivities of 2.7, 2.8. Crazy sometimes. So that all worked out so far.
Well, one more question.
Yeah.
You said the rest of the buildings are on steam, right?
Mm-hmm. In
this design, did you incorporate any kind of heat recovery from the condensate that was coming back?
No, they actually reduced the size of their steam boilers based on us taking the load off. And they were afraid that now they didn't have, they would lose too much energy. They would have to, you know, I suggested that if they want to do that, but they feel that's just not waste heat anymore. They need it so they don't have to heat it up again.
Gotcha.
Yeah, so I had that discussion with them, otherwise I would. But now because they don't run it in the summer, and I wasn't too concerned about it because keep in mind, New York City has a unique thing. The entering water temperature in the wintertime drops down to 40 degrees or even a degree less. However, in the summertime, it's 75. The hot water, the cold water supply.
Yeah, we've logged that and discovered the same.
Yeah, so it's kind of weird. You have all those fluctuations. So the loop field will actually draw down to about 32 degrees, and probably in the summertime it runs at 34, 35, something like that.
So it's always in that 30 to 35 range.
I'm sorry, the loop field for the source side of the heat pumps. The cold water supply is anywhere between 39 and 75.
Right. But what's your temperature band on the bore field itself?
I mean, we standardized it, so we designed with the worst scenario there, and then we did all the buildings the same. So they have a standardized design.
32, 34?
So some of them are a little bit oversized, but between 32 and 35 degrees, the loop field will run all year long. Yeah.
Thanks.
Which one?
Hang on.
Which one? The question was, how do we balance the flow rate? And then that flow rate goes up and down. So this is a very sophisticated control. That's where, you know, and the question is now, how do you slow down the flow very quickly or increase it very quickly? And it's a combination of very smart pumps, which can do that, but also a valve which opens and helps you control that flow. No, just like sourcing the right materials, like what's your opening time of your valve, let's say, or how quickly does the pump rev up, and where do you, I mean, it's really gets down to where do you place the sensor and how do you place it there. Don't do it 10 feet down the pipe. You follow me? So this needs to be, this is tricky, but it's you can do amazing things in terms of efficiency and performance once you control the settings which you place your heat pump under. So that's really where I believe the future is. It takes an in-depth knowledge. You can always put, I mean, I told him, I said, look, worst case scenario, we're putting 10 little heat pumps there, modulated, and have a whole bank there and have like 20 of the indirect tanks. What's the deal? Yes? Oh, yeah, go ahead.
So this geothermal system is only for domestic heating, no cooling,
It's
right?
only for domestic, yeah.
So did you look at the ground temperature drift?
Mm-hmm.
Because you are heating over 10 or 20
Sure.
years?
Yeah, it's sized for that.
Size for that?
Yeah. No, it's unusually large. It's about 65%, two-thirds oversized. Okay. Yeah, you have to do that because now you never put heat in, you always pull it out. The good part is now if they want to put the rest of the building in, they only need a few additional boreholes. Because now they have a balanced loop field, hopefully, we'll never know. And so anyway. Yeah.
Hi, Aaron Flack from Nile. I'm just curious, in the previous slide, you were describing it sounded like you were describing an instantaneous system.
Uh-huh.
But in this slide that was just up, that's a completely standard single pass arrangement with storage. You said that there was no storage previously, I thought.
Well, not really. The storage doesn't really help you that much more. It doesn't get you over the 12 hours of peak use. I still like to have some storage tanks there.
But I guess I'm unclear what the advance is here because 6 gallons per minute with that kind of bore field and this kind of equipment doesn't seem that unusual.
Well, I would argue it's relatively unusual to have a single pass-through instantaneous 30-ton heat pump making instantaneous hot water.
Well,
It's
how
kind
much
of
storage
unusual.
do you have?
Huh?
How much storage
Oh,
do you have?
we have 1,500 plus 300 in this passive tank here too, which we don't turn on.
Okay, so you have 1,500 gallons
so
of
about
storage
1,800 gallons of storage. Yeah.
and how many 30-ton units?
2. 2. 60 tons.
Okay. That's impressive.
Yeah.
I'll give you that.
But they're instantaneous, that's the key. Yeah, that's kind of the fun here. Anyway, the reason why we don't want too much flow through this, we don't want to disturb anything in here. We don't want to flush the tanks and create turbulences in there. We want as little flow as we can there. We want cold water to come in, and this tank suddenly is at 40 degrees, but up here it's still at 140. The tank is stratified. You don't want to disturb that. And pushes slowly the hot water out. And then it flows in, it refills from the other side, and pushes the cold water out again. And then you have a little temperature sensor there, and when this is satisfied, the heat pump shut off. Or they stage off. So, anyway, that was our approach. I'm saying there are other approaches, but I was intrigued by the possibility of making instantaneous hot water, not mixing the hot water, and achieving an unusual high COP. If you run this heat pump under normal conditions, your COP of making 140-degree water is probably running around 2.2. You know, so I was savvy, and I thought, geez, if I can now get 50% more efficiency out of it, wouldn't that be cool? You know, yes. Okay. Anyway, so Zero Place. One of my favorite places, as you know since this morning. Won a lot of awards. Governor was there. First building of excellence by NY-GEO. Very efficient building. They really went the extra mile. As I told you about this morning, about 46 residential units. Was 100% privately funded. This is, by the way, Dave Shepler. He is the CEO of an AI company. He was the director of the Watson project at IBM. So he's doing geo for fun, kind of. He owns buildings, and he wanted to build the best system we can build, and we did all this. So this is kind of the utility room. Again, here we have 2 heat pumps there because the load is smaller. We have 2 load pumps here. This is the entire building. Every unit has a heat pump, which either heating or cools that building. And then we have 4 of those storage tanks here. These are 162 gallons indirect tanks. There's no backup here. We are very confident 1 heat pump can carry the entire load. And we use that preheat and final heat design, which we came very accustomed for. Everything is double redundancy. The smart pumps, the Velo variable speed pumps, they only pump as much energy as you need. This entire building, average pumping power, 400 watts. Only 1 pump runs. They talk to each other. They alternate each day. 1 pump can carry the entire load. The other pump is only there for redundancy. Maximum pumping power, 500 watts. Pumping power is less than 1.7%. But this is not just for the hot water, this is for the whole building. But it cools that building, so the loop filter is never over really 75 degrees. Which also means we can use methanol as a heat transfer fluid, which also means it's easier to pump, which then also means there's lesser heat ending up in the loop filter. And it's a much better heating transfer fluid than glycol is. So this runs on an alcohol. And like I said, the average for the first tank is about 3.7 and 3.0 on the final tank. So they average out about 3.3. Pretty good too to make hot water. This is their profile. Now this is market rate. They have like 5 affordable housing units in there. This looks normal. This is normal. This is about 1,300 gallons per day on average. This is not affordable housing. That was almost boring to design because it was so normal. It was not like nature, so. But we like challenges. And you can see here, this is the morning between 6 and 8. This is the evening. This is all the data is monitored by NY-GEO. They want to do the grid planning with this data. They want to know what they're up against. And they don't trust anybody, which is good, so they monitor and verify it themselves. But that also makes the data very legit. And this just exemplifies here now the daily ground loop loading, we call it. And look here, this is heating, this is cooling. Did I get this wrong? Loop load, MBTUs, that's a load on the loop. So we are injecting something here, this is where we extract. So, this is the entire profile for the entire GEO system in terms of energy use, kilowatt hours. The yellow one is all the hot water. It shows you that it can be substantial, even in a market rate apartment which is not over-occupied. In the shoulder scene, this can be almost 50%, 40, 45. That is a dead normal building. And of course, the energy use, I mean, it doesn't go to zero. You don't have this typical shoulder month anymore for heating and cooling. Believe me, I have tenants in there. They run their apartment at 63 degrees and they cool it all year. They never turn the heat on, ever. It's just the internal gains that a building like this has. So. But that was all good. That is the annual month, this is the average monthly profile here. You can see this is pretty dead even. Roughly about 1,200 gallons plus minus 200 gallons, 150 gallons. So this is predictable, this is great. Like I said, New York City, whole different ballgame. And this is just reflecting the higher efficiency once your loop temperatures go up in the end of the summer, like September, August, September, when you start ejecting the air conditioning you need into it. And then it goes down again. So just profiles you have to be a little bit aware of. So the moment the loop fill gets heated up again, and the heat pumps actually have to keep it cool. Very important. It was interesting, a fun project here. Because can you use the microphone a little bit? I'm sorry. This is the peak. And I remember we had the plumbing code tells you to put, 4-inch lines in there? Or 4-inch piping? Well, the highest peak we ever recorded was 8 GPM. You don't need a 4-inch pipe for that. You actually have a lot of energy losses that way. That building was using about 28% on the recirculation line. Huge amount of energy loss. So we actually measured about a 0.13 GPM peak usage per apartment. So if you have 100 apartments, you're about 13 GPM. So it kind of taught us different, again, whole different ballgame then. If you think this is a great design guide and then you get into affordable housing, whoa, very different. So we played around with it and said, let's reduce the flow on the circulation line because we don't really, they used to run it at 9 GPM, circulation line, and we dropped it just to 4 GPM. Let's see what happens. Well, what happens is that these are the temperatures. They actually went up leaving the tanks because we did not disturb the stratification of the tanks as much. So the supply temperatures actually went up. The return, due to this lower return temperature, actually went down a little bit. But that's only temperature, but multiply that with a flow, and you started up to reduce the energy usage for the circulation line or the losses by 23%. That was, these are megawatt hours. These are 4 megawatt hours per year, which we're saving. All we did is go in there and shut down the valve a little bit. Just tells you how we're overshooting with some of our design, and we can be so much more efficient if we really study this in granularity. So the entire COP for the domestic hot water increased by 11% because of that. And again, that equaled out to about close to 4 megawatts. It was huge, megawatt hours per year. We're talking megawatts, not kilowatt. So that was substantial. So, in summary, we can make 140-degree water. We got to be tricky with that. And the heat pump designs is evolving. We get new refrigerants. We learn a little tricks, run the tanks in series, not in. We need to be better with the controls. We need to be faster reacting. We need to understand under what conditions we put the heat pumps on. But we can do this. That's not the issue. It's just an engineering feast. But is it necessary? That's the other question. So I'm a little critical of all those guidelines, and I was asking the question where we're coming from, and there's really not a good source. Somebody was on a committee and had an idea and said, this is how we're going to do it now. But there is no must-do thing, unless I'm missing something. NY-GEO might say that because they don't want a liability either. And they're saying, oh, by the way, there's a CDC guideline out there, so let's do that. But the CDC guideline has no backup. So, for us, the staging of the tanks was cool because it just increased the capacity, but also the efficiency of it. It was worth for us. Again, I'm pointing out that the integration of the domestic water is almost necessary. It makes the system so much better performing because you control this runaway and this daily addition or yearly addition of increased temperature when you have unbalanced loads. And they all go up, they never go down. So it's always cooling dominated. And I'm saying, hey, the equipment is for free, why wouldn't we do that? We save so much on the loop field. And then, you know, the attention or the trick is be aware of the stratification. Do not mix cold water in there. Do not mix cold water going into the heat pump. Do not mix cold water, if you can avoid it, going into the tanks. You destroy all your stratification. So, and you know, I think this is going to be, it has some potential. You can have a very smart design, but oh boy, you got to be over the controls. It's not that easy. It's not that. It's almost counterintuitive what we knew about heat pumps. Let's starve them. Let's make them slower. Let's raise the temperatures, and they're running more efficient. Wait a minute, how does that work? But that's the way it is. It's possible. So anyway, questions? I don't know. I threw some up there because it's required by the credit-given entity, but I rather open it up to you guys to say, what are your questions?
We can do that.
Hey.
Questions?
I just want to clarify that, excuse me, as far as I know, the NY-GEO requirement to produce 140-degree hot water is entirely driven by the CO2 heat pump manufacturer lobby. They've constructed the guidelines that only CO2 can satisfy that requirement.
Yeah. And I'm not sure, I mean, why would NY-GEO set a rule? It's not really there.
Well, to receive their incentives.
Yeah.
They're not setting a rule in the code, but to receive NY-GEO incentives, your machine has to be able to produce 140 degrees.
Okay, we can do that, but do we need to run it on?
What's that?
Do we need to run it at that?
Yes. Well,
Okay. One day. Here's my point. I mean, NY-GEO should not be the authority having jurisdiction. Don't get me wrong, I love NY-GEO, I love all the guys there, we work with them. We couldn't have done all this without them. They're monitoring this, they're helping wherever they can. But they are not the health authority, nor do they are code enforcing an authority. Well, it's not their money, it's the utilities' money, and they don't make that money. So NY-GEO really has nothing to do anymore direct the utility program. Yeah. I mean, I never thought about it because I want the heat pumps, when we are using them even at 125, I want them to be at peace. So we use like, you know, vapor injection, or in this case, liquid injection, or we use, you know, and most companies come out with it. They've mastered that down. You heard EcoForest, you heard Climate Master, you heard, you know, they all realized that there's an issue with the hot water. And why would you either make it with electricity, you go crazy? Would you make it with an air source heat pump? The grid will collapse also on the coldest day of the year, or they wouldn't even make it. Or you have ground source. It's really the only technology, in my opinion, you have where you have a constant, you know, constant quantity of energy coming in, no matter how cold it is outside. So I'm a big fan of it, and like I said, it keeps the loop fill so nicely at balance. But you got to make sure you don't have, I mean, you've seen the systems where you walk in and somebody has variable speed heat pumps, and because something isn't working, they turn them both on, running in parallel, and they put like, you know, 12 kW of heat energy into the loop field, 24/7.
Just out of curiosity, when you started working on the Jackson House process, was there a requirement for air source heat pumps? Because I've worked on 20 projects for NY-GEO, and they ruled out geothermal right from the beginning. They were not interested in talking about that.
No. How else would they make the hot water with heat pump
You're
technology?
clearly much more charming than I am.
I don't know. I never heard that. Actually, I think they're very intrigued with what this does for them. And I mean, no. I mean, why wouldn't you put Geo there? I mean, I was joking around and they laughed about it. I said, look, you have park-like settings around your buildings. You have room. Whoever designed your developments in the 40s clearly had geothermal in mind.
Wasn't the shoulder blade?
No.
Other questions? Good. Okay, it is the end of the day, and we won't hold you here. First of all, I did not let you know that anybody who wants CEU credits, please come up to this table. If you've registered in advance, we've got your name. All we need is a signature. If you didn't register and you want the credits, then you have to fill out a couple more lines. But with that, I will ask you to give our NY-GEO president another round of applause. And thank you for all you do, Jens. You're a real asset to our
Let us
organization.
know if you have any questions, or you need help, or you need tips, or you need, I mean, you're all seasoned people. But I thought it's a great discussion to have, because I think the field lacks a little bit of knowledge on how to integrate all this down the road. So, but it's coming, it's necessary, specifically when we're trying to get 100% off everything. So, and the hot water, which used to be the highest mark, or the highest challenge, actually is the easiest one when it comes to the most cost-effective one. You get the biggest bang for the buck. Because again, we don't have to go into the tenants' apartments right now and put heating and cooling in there just for them to achieve that goal. It all changed now. This whole project started before the Inflation Reduction Act. Now NY-GEO qualifies for direct payment. Now they get up to 50% subsidies to it. Things change. Suddenly they're more Geo everywhere. So, anyway, all right, good, thanks.